So we are about to finish this section today. Tomorrow we will invest our time for some problem solving, and if you have any queries related to the topic, tomorrow we have 2 hours time for that.
Can you please upload
And yes, somebody, any query?
these random variable
Please be louder.
Hello sir.
Yes, yes.
Sir, kindly upload these random variable PDFs we sent
Ah,
below into.
this is already available in your MS Team.
PDF.
Sir, this
Yes,
uploaded
this PDF, right? Is it not available?
No, sir, the earlier PDFs were not available except for the class 1 PDF.
No, no, wait. कहाँ गया? Teams. So if you go files, there is class material. And this is a PDF called Proba. Have you checked it?
Sir, it is not till it is up to 34.
Random variable up to page number 17. You see, it is updated last week. Please check it and let me know. I will keep this file with this name and I will keep on replacing it. And I will try my best before starting any topic or any chapter, I will upload its complete PDF with all the details. Please check and let me know whether you have the access up to this much.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Thank you. चलो तो क्लास शुरू करते हैं. Okay, so in the last lecture we have introduced mean variance and in general moments. So today we will see some more new aspect of the moment, and first of all we will define mean in a different way for non-negative valued random variable. So if you have random variable which is taking value from 0 to infinity, it might be discrete, it might be continuous, then you have the flexibility or advantage to compute that theoretical expectation with a different formula which is given here. Expectation of x equals to summation k running from 1 to infinity probability x greater than equals to k. And here you can see the right hand side, each of the term is 1 minus CDF. So CDF is probability x less than equals to something, it is just the reverse complement part of that. So with that function you can write down the expectation. So this is the general form. That number. Okay. Let x be a random variable with probability x greater than equals to 0, that probability is 1. Okay, so it is always greater than equals to 0, non-negative. Then expectation of x can be defined in this way if exists, that sum over k running from 1 to infinity probability x greater than equals to k if x is discrete, and integration probability x greater than equals to t dt 0 to infinity if x is continuous. So I will show you this thing, but I will have give you as a homework for this one, and as well as the formal writing of this, so that you can get it mathematically correct. I will try to give the interpretation of this expression. So let us try to see that. Suppose consider, and it reduces the calculation a lot. It is really helpful in many situations, that x is discrete and fx, or say probability x equals to small x and equals to, you can write px or something like that, where say x equals to 0, 1, 2 up to it is going on. Now what do you know about its the definition of expectation if expectation exists? So expectation of x is sum over x px x running from 0 to infinity. That is by definition. Okay, very simple. Now I am writing this expression in a different way. So what does it say? First of all, let me write it down, that it is saying in this way. So 0 into P0 plus 1 into P1 plus, I am writing vertically, I have a purpose, 2 P2 plus 3 P3 plus 4 P4 and so on. This summation is going to infinity. Okay. Now the same thing I can write in this way: 0 P0 plus 1 P1 plus 2 P2. I am writing P2 plus P2. Then 3 P3, I am writing P3 plus P3 plus P3. Then 4 P4, I am writing P4 plus P4 plus P4 plus P4 and so on. P5 5 times, P5 plus P5 plus P5 plus P5 plus P5. Okay. And now if you just try to see it. Okay, so P0 into P0 doesn't have any contribution. I can throw it away. Now try to see this thing, entire thing. If you write down, what will be this quantity if I, instead of adding them horizontally, if I add this column first, P1 plus P2 plus P3 plus P4 P5 and so on, what does it mean? What probability will it give?
Probability
P
that
of
x
x
is greater
greater
than or
equal
equal
to
to
1.
1.
Probability x greater than equals to 1. So probability x greater than equals to 1. Similarly, if you write down, calculate this probability up to infinity, what will you get?
Probability x greater than equal to 2.
Probability x. Similarly, this sum will give you probability x greater than equal to 3. This is greater than equals to 4. This is greater than equals to 5, and so on. It is going on. So probability x greater than equal to 3 plus probability x greater than equal to 4, and so on. So can we write probability x greater than equals to k running from 1 to infinity? That is what we wanted to say. Is it okay?
Yes, sir.
Now I am leaving this, showing this to think with formal mathematics. This is how its interpretation is, and this is equals to this. Formula wise it is all right, interpretation wise all right. Write down it in a formal mathematical way. So what I mean here in this thing, say expectation of x equals to, here with this notation, so it is sum over x running from 0 to infinity x px. So here you can write in this way that, okay, so 0 part you can also neglect, it is 1 to infinity x px, it doesn't matter. Then this x you can write in this way, x running from 1 to infinity t running from 1 to x, and here you have 1 px. Is it correct?
Yes, sir.
Is it okay for everyone?
Yes, sir.
Yeah.
Yes, sir.
Now interchange the order of summation. This part I am leaving to you. Interchange the order of sum. Take this one out, take this one in. So whatever necessary change you have to do, you do it. Same thing will happen for this. Instead of summation, you will have integration. You need to do the order change of integration. I hope you have done several variable calculus little bit in your double integration. At least you have done in your math 1, math 2. So let us see. If you cannot do, tomorrow we will do it. So give it a try. Now, if you want to take the help, Whale, Port and Stone. This book can help you. Many other books can help you. This is a very standard result, and you can see it is a pretty simple result, but it is a very useful result also. So okay, so we will do this example of this theory tomorrow. I am just postponing all the mathematics, the problem solving for tomorrow, not today, so that we can juggle with the theorems. Okay, now we are going to define another important aspect, which is known as the moment generating function. So moment generating function is typically a function, and it has the advantage that if you know the moment generating function of a random variable, you can extract any order moment from that moment generating function. So that is the advantage. And second advantage is this: if the moment generating function exists, then it also uniquely identifies the probability distribution, so that you can get back the CDF as well as the PDF or PMF, and at the same time the moments. So we have stated that CDF is uniquely identifies a random variable. Then PDF or PMF also uniquely identifies the random variable. Now also we are saying that moment generating function is also uniquely identifies the random variable if moment generating function exists. Okay, so now we are defining it, and we will try to see what are the interpretation and how you can extract the moment generating function. So here we are going to define it. So let x be a random variable, so MGF, moment generating function. Let x be a random variable such that expectation of e to the power tx. Note this thing, this is finite. X can be positive, negative, continuous, discrete, doesn't matter. E to the power tx is always non-negative. Okay, and for some t, okay, so for all t belongs to minus epsilon to plus epsilon, where epsilon is positive. So minus epsilon to plus epsilon, where epsilon is positive. That means in a narrow range around 0. You will see why we need narrow range around 0 with an open interval. So if this quantity is finite, then we define the moment generating function of x as usually written as m suffix x within bracket t is expectation of e to the power tx. Okay, and also we need to write that t belongs to minus epsilon to plus epsilon, epsilon greater than 0. Okay. Now immediately you can do the expansion, Taylor series expansion of this quantity. So what you can do is you can expand it, k running from 0 to infinity, tx whole to the power k divided by k factorial. Okay. Now, as this is given, this quantity is finite, we can take the expectation inside. Actually, the order change is a very delicate thing. Sum of the limit and limit of the sum always need not be equal. So when it is guaranteed, then only you can do the order change. Okay. So this is known as the Fubini theorem that you might come across later on in your mathematics course, but that is needed to be done. Okay, so k running from 0 to infinity, expectation of t to the power k, x to the power k divided by k factorial. So notice only x is the random variable part, t to the power k is constant, k factorial is constant. So you can write this quantity again, that this is sum over k running from 0 to infinity, t to the power k by k factorial. Okay, tell me, if I take expectation of x to the power k, whether it will be raw moment or central moment?
Raw moment.
Raw. So mu k prime. So it will give you the raw moment. Okay. So now how can you extract this any order moment from this infinite series. So you have a collection of all moments. Doesn't matter. So how to extract out, say, rth order raw moment? What you need to do?
Sir, rth order differential at x is equal to 0. At t is
X
equal to
not t equal to 0. So first you differentiate. So to get rth order raw moment, differentiate this thing del t m x t. So what will you get if you differentiate it? What will you get? Okay, so any order term less than r will vanish. Is it okay?
Yes, sir.
T to the power k in this form it is. So any order term, so del t to the power r. So r times I am differentiating. So any order term less than r will vanish. So starting from the rth order up to infinity will be there. Okay. Now if I put t equals to 0, I am differentiating at putting t equals to 0. So only the rth order term will not contain t. All the higher order term greater than r, they will contain t, but if I put t equals to 0, they will also vanish. So remember this thing. So here is r. This part will vanish 0 for differentiation, and this part will vanish 0 for t equals to 0. So only the rth order term will have the contribution. So how much it will be? So if you differentiate successively, it will be r factorial, and it will become denominator you will have r factorial, and here we will have expectation of x to the power r. So that is mu r. So this is how you can have the any order moment if the moment generating function is known to.
Sir, shall we write del to the power r by del t power r or del by del t power r?
Okay, yeah, no, del to the power r. Yes, I just messed up with it. Rth order difference.
Sir, there is sigma. How do we differentiate, sir, when there is a sigma? Normally, when there is a sigma, we find the equivalent function of the sum, then we can differentiate that. But inside the sigma, it's like each and every term are different, where you put the k value. So there, how do we differentiate, sir?
So you need to take the differentiation to each of the term.
Then each of the term will have some fixed value of k.
Yes, I am differentiating with respect to t. I am not differentiating with respect to k.
Okay.
I am differentiating with respect to t, not k. Do you get my point?
Okay, sir.
Hello? Hello?
Okay, sir. Hello.
Yes. Any other query?
Yes, sir. In the sigma, you took expectation of t power k x power k by k factorial as t power k. You took the t power k outside, right? If there are some constants, can we take out like that?
Yeah, if you have expectation, already we have discussed about it, man. Right. No, not here. Yeah, that is trivial because what you do from the definition. So that is trivial from the definition, that if you have expectation of a into x, that means a into x into fx dx or summation or integration, whatever. So a you can take out. Is it not trivial?
Yes, sir. Okay.
But if you do the variance, it will be a square. Remember this thing. If you take the variance of ax equals to a squared times variance of x. If you go by the formula, you will get it. 2 lines job. Okay, now I am leaving with 2 remarks what you should not forget. First one is trivial to understand. Second one might not be trivial, but we will not be able to give example in this course. Okay, first one is, if the moment doesn't exist, already you have seen where it is. No, I have given you 2 exercises. Yes, these 2 random variables, one is continuous, another is discrete. Moment doesn't exist. So if the moment doesn't exist, moment generating function also doesn't exist. Okay. So if the moment doesn't exist, if the moment doesn't exist, MGF doesn't exist. And second thing, even though all moments exist, the MGF may not exist. The example can be constructed, but it requires, and for the proof, it requires another notion that is known as the characteristic function, which is a Fourier transform. So that is not in your syllabus, so we are not going for that. But remember these 2 things, that moment doesn't exist, then the moment generating function will not exist, there is no doubt. But there can be example where all moments will exist, but still the moment generating function will not exist. That means this quantity will not be bounded. Okay, that can be done. Okay, I am leaving this one as a remark only. Okay, now based on moments, we will have few important inequalities which are fundamentally important in the course of statistics as well as probability and stochastic process also. So one important inequality is the Markov inequality. And it is a pretty simple looking, innocent looking, but it is powerful, very much powerful, because its implication is huge. So let me state it. So this one, probability x greater than t is less than equals to expectation of x divided by t. T is greater than 0 and probability x greater than equals to 0 with probability 1. So t is a positive constant and x is a non-negative valued random variable. Okay. So if this is the situation, then we can have this inequality. So the proof is pretty simple. Let us do it, because the idea of the proof will be implemented or used again. So I'm using continuous valued random variable for the sake of the ease of notation. So expectation of x, what you know, 0 to infinity x fx dx X is the random variable, fx is the PDF. Now I can split it into two parts. T is greater than 0, so 0 to t. This thing you know from the Riemann integration, x fx dx plus integration t to infinity, again x fx dx. So this is pretty simple splitting of the integration into two parts. Now you see x is non-negative, fx is non-negative, so this integrand is non-negative, so this entire quantity is non-negative. Okay. So if I drop this part, what I will end up something less than or equals to t to infinity x fx. Okay. Now again, this is a function which is of the form x fx dx. Now, and x is increasing. So if I replace x, then also I will end up x with t, which is the lower bound, then also I will end up something less than this. Now you notice what is this thing? T integration fx dx. So what is this quantity? What is this quantity?
1.
Say again, please.
Probability greater than or equal to T.
Probability. So this is equals to t times probability x greater than t. So this one, this inequality, this result. So you will ultimately end up with this, that probability x greater than t again, don't forget x is greater than 0, greater than equals to 0, and t is strictly greater than 0. This is known as the Markov inequality.
Sir,
Now,
why not x greater than or equal to t, sir?
Because I have used continuous, so if you write equals to, the probability is not going to change. If you write is equal to that, then also probability is not going to change.
Yes,
Because already by definition at each point the probability is 0 for continuous value.
yes, sir.
Okay, now we are going to use this result for another inequality which is known as the Chebyshev inequality. So let me just give you the statement first. Yeah. This is the Chebyshev inequality. X minus mu greater than epsilon is bound, that probability is bounded above by expectation of x minus mu whole square divided by epsilon square. So just I'm copy pasting this thing. Okay, so maybe I can go for the next page. So I'm just copy writing once again, and it has a huge interpretation. Maybe you have already seen it but not noticed it. So first square, then expectation, definitely, and y divided by epsilon square. So we are going to prove this one. Okay, so to prove this one, we need Markov inequality. But notice one thing, that we have not claimed anything here whether x is positive or negative. x can be any random variable, provided, so provided expectation of mod x is finite, or maybe I am writing this thing mod x square, or maybe expectation of x square only you can write. No need to write mod x square, only expectation of x. Second order moment is finite. That means second order moment is finite. So another interesting homework I am leaving for you. So if here I will, that if the rth order moment exists, then all lower order moment exist. Simply, if rth order moment exists for x, then all lower order moments exist. So that means if expectation of mod x to the power r is finite, then expectation of mod mod x to the power s is also finite when s try it, 2 lines proof. Okay. Now we are going to prove this one. Remember, we have not claimed anything about the positive or negative random variable. We have just claimed that the second order moment is finite, and that will tell you the mean is also finite. Mu x is expectation of x is also finite. Okay, so now tell me how to prove it. How to prove it? You need to use Markov inequality. Any clue?
Sir, can we divide the LHS into two parts? That is,
Okay.
x minus mu x is greater than epsilon and less than epsilon, and sum those parts and then apply Markov inequality to both the parts.
But the non-negativity is not guaranteed yet. You need to bring the non-negativity first.
Sir, in Markov inequality, if we take x as mod x minus px and t as epsilon,
Okay,
we'll
okay. Yes, go ahead. Go ahead, please. Say.
yes, sir. If
Go
we
ahead.
take from Markov inequality, if we take if we replace x by x mod x minus mu x, I mean, if we take mod, then we that part is greater than 0 is guaranteed, and we take t to be epsilon.
Okay, thank you. Yes, that is the right approach. So let us define y equals to x minus mu x mod. So that means y is greater than 0 and epsilon is greater than 0. Let us consider. Then notice this thing, probability x minus mu x greater than epsilon. Here is another catch, is same as x minus mu x whole square greater than epsilon. Tell me if anybody has any query or any doubt that these two probabilities are same.
Sir, mod epsilon.
Epsilon is positive. No need to take mod.
Yes, sir.
Anything else? Anybody? Any doubt? You see that when you consider the positive part of real axis, then this is 1-to-1 function, x square. Is it okay? If you take minus infinity to plus infinity as domain, x square is not 1-to-1 function. But if your domain is from 0 to infinity, then it is 1-to-1 function. So here maybe you can write it y, then it will be more convincing for you. So y is greater than epsilon, y square is greater than epsilon square, saying the same thing because y is positive. Is it okay for everybody? Any query? Okay, pretty simple. Now you consider that this quantity is non-negative, epsilon square non-negative, implement Markov inequality. हो गया काम खत्म. Now notice this thing. What is the meaning of this numerator? What is the interpretation of this numerator? This is in general true, but what is the expectation of x minus mu x whole square? What are the other name you know of this expression?
Variance.
Variance.
It is variance of x. Usually you can write also sigma squared x by epsilon square. Okay. Now,
Sir, could you please explain once again that how the probability of mod of x minus mu x greater than epsilon is equal to the probability of x minus mu x square is greater than epsilon square?
so if you consider y equals to x minus mu x, y is always positive. Is it okay?
Yes, sir. Yes, sir.
Now, if you have y on the positive part of y-axis and you consider a function y square, then it is a 1-to-1 function. Is it okay?
Yes, sir.
Now, if I say y greater than epsilon and y square greater than epsilon square, is it not representing the same set of y? The value of y for which y is greater than epsilon and value of which y for which y square is greater than epsilon square, where already you know y takes only positive value, non-negative value.
Yes, sir. That is the same thing, but the y square is another kind of curve, so it is exactly the same function. How can we say that?
What is your notion about 1-to-1 function? You will have unique image, right? And
Yes, sir.
So whatever y is satisfying this condition, the same y will be satisfying this condition. Nothing extra anywhere. And
Okay, sir.
if two sets are same, the probabilities are same.
Yes, sir. Yes, sir. Understood.
Okay. Okay, so this is the way, and its complement part also can be written in this way, that probability x minus mu x less than epsilon, this is bounded above, bounded below by 1 minus expectation of x minus mu x whole square divided by epsilon square. This expression is also useful. This is just taking 1 minus to both sides. Or you can take the, okay, you write here in greater than, you can take it less than equals to, doesn't matter. So now what it says, let me try to draw it, that if you have a distribution, need not be so well behaving, but let us see more or less. So you see that here is suppose the mean mu x, and here is mu x plus epsilon, this range is epsilon, here is mu x minus epsilon. So what it is claiming, if you see by this, if epsilon is large, epsilon is going to infinity, this quantity is going to 0, because already we have assumed that the second order moment is finite. So the numerator is finite, denominator is going to 0. So probability is always bounded above by 1, and here it is bounded below by some quantity which is going to 0. So by Sandwich theorem, this probability will be going to 1. So if you consider this section is considering the the within part. So if you take epsilon large and large and large, so it will incorporate the probability more and more and more. If you make it even more thinner, then definitely it will contain less amount of probability. So this is the idea of Chebyshev inequality. Now okay, so interpretation, as an interpretation, how much time? Okay, so as an interpretation, so if the random variable has variance increasing with sample size, decreasing with sample size, then you will always observe that the variation, the fluctuation is less and less and less, and it will be centered around this point. So as an example, if you just consider, already we have seen this one, yeah, you can see that when I am doing the estimation with more and more sample size, its fluctuation is less. So fluctuation is gradually less over the increase of sample size, and sample size increases means the variance also decreased here. So as sigma square decreases, this quantity is going to stick to the true value. Again, here in this example also you can see, oh, okay, yeah, first initially there is a huge fluctuation, then gradually it has almost zero fluctuation. But well, there will be some number, not exactly zero. Fluctuation is there, but the amount is less. So this is what you have already seen, but may not be in perspective of this notion of Chebyshev inequality. So this inequality says that as this sigma square part, this numerator part, eventually the numerator part goes to 0, with a high probability it will be stick to the true number which you are targeting to access or approximate. So increasing the sample size is a very essential thing in this aspect. So we will have a formal proof of this result, same proof, 2 lines more extension, and the theorem is known as the weak law of large number. Okay, so maybe after few lectures we will go for that. Okay, now before we go any further, let me briefly tell you few more things related to moments, which are important to know. These are descriptive part. This comes from in the part of descriptive statistics. Okay, so let me just. So if you consider, so first of all, expectation of x, if exist, is the mean. Okay, then x such that fx, which may be PDF or PMF, is maximum is known as the mode of the distribution, mean of the distribution. So that means if you have PDF or PMF, whatever, so x for which fx is maximum, okay, it is not the maximum value of x for which fx is maximum. So eventually you can write mode is argmax, that means maxima, not maximum, argmax x fx. Fx can be your PDF, PMF, doesn't matter. So this is first, this is second, and the third is median. Median is, say, xi. So probability x less than equals to xi is okay. So if it is discrete, so if it is continuous, let me write x greater than equals to xi. If x is continuous, and probability x, and that is half trivially, x less than equals to xi is greater than equals to half, and x greater than equals to xi is also greater than equals to half. Then if x is discrete, then xi is called the median of the distribution. And these three measures, median, mode, and mean, they are known as the measure of central tendency.
Sir, can you explain the second point once again?
Yes. This one or this one?
Mode.
Mode one. Okay, so mode one means, suppose you are trying to make a T-shirt for your classmates with stamp and logo and everything, but different candidate will have different size of their shirt. So which size will you go for? Okay, so you will go for that size for which the maximum number of students will prefer to have it, right?
Yes.
So this is the height. So if you draw it in a discrete sense, so maybe say this is the size, maybe say 26. This is for 30. This is for 34. This is for maybe say 38. This is for 42, and so on. So you will go for this 34. Maximum number of students will be interested for this one, and maybe whoever has size 30 or 32, they will also go for 34, and whoever has size 36, they might also like little bit tight also, they can go for it. So if you have this kind of restriction that you can build only, your vendor can probably produce only one size, then only one representative which will attack or target the maximum proportion. That is the idea of mode. Is it okay?
So that argmax, what does that mean?
So argmax is the argument of the function for which it attains the maximum. Okay, so in other words, it is maxima. Okay, argmax is equivalent to maxima. Is it okay? X
Yes.
for which fx is maximum. Argument of the function for which the functional value is maximum.
Okay. Sir.
Okay. So another interesting thing that few distributions are of like this. This is this kind, or maybe this kind. So the way the longer tail of the distribution, so this is known as positively skewed, and this is known as negatively skewed. So if the longer tail in the lower direction, negatively skewed; if the longer tail in the higher direction, positively skewed. Now in positively skewed distribution, mode comes first, then the median comes, then the mean comes. So mode, mean, median. And here just the opposite. Mode is, these are the empirical thing what I am saying. And median, sorry, mean is highly affected by extreme values. So say for example, in your, if your class, so you can see that if your class, say for some guy is, you are studying their height distribution, some guy is say around 8 feet tall, your mean will be shifted to the right hand side, but it will not hamper the median, because 50% data above, whatever you want to do with that above 50% doesn't matter, it will affect the lower 50%. So median is often termed as the 50% breakdown point. Okay, forget about that. But mean is highly affected by extreme values. Remember this thing. Mean is highly affected by extreme values. Extremely positive, extremely negative, both. But median is not. So that's why often median is a more stable approximator of the central tendency compared to the mean. And how to get median? You have the data, sort them. If it is odd number of data, take the middlemost. If it is even number of data, take the middle two and take whatever way you want to take the average. That's all right. So having median is very easy also. So I think I should stop here. Two more things I had to say about this skewness and kurtosis. Maybe let me just quickly, 2 minutes I will take. Do you have class? Okay,
Yes,
so
sir.
okay, then tomorrow we will do. Just two definitions left. We will discuss it tomorrow. Skewness and kurtosis. Our
Excuse me, sir.
yeah, bolo.
Can you please just explain these two equalities and inequalities, that the p of x is less than epsilon is equal to the half value, but I can't understand how the
This one.
value is. Yeah,
Okay.
yeah, both the
Okay.
this and
So if x is continuous, whatever way, no problem. You will find some xi, and the area under the curve, this side is half, and the area under the curve This side is half. So you need to solve this integral equation minus infinity to xi ft dt equals to half, and at the same time xi to infinity ft dt. So whatever is the solution of this equation, it will give you the value of the median, or in other words, say if xi equals to 0.5 equals to 1 minus f. Same thing, writing whatever way. If xi. So if xi equals to half, only one equation you have to solve ultimately. No, doesn't matter. Now if it is discrete, the problem is this: you have mass function, you have no scope to integrate. So it may so happen that, say, this is for 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and these are the probabilities. Okay. So if you add probability for 0, 1, 2, 3, 4, okay. Now if you add probability x equals to x, sum over x running from 0 to 4, you may find that you have just crossed the 0.5, and from the back, so if you leave 4, if you go, but probability x equals to x, x running from 0 to 3, it is strictly less than 0.5. So it is not reaching the 50%. It is less than 0.5. But if you incorporate the fourth point, the 4, probability of 4, then it is exceeding 0.5. On the other way back, if you take the sum of x equals to, say, 4 to 9, then also you are exceeding 0.5. But if you are taking the sum x equals to, say, 5 to 9, then also you are not reaching 50%. So 4 is such a point, if you incorporate to the lower half, it is exceeding 0.5. If you incorporate in the upper half, it is exceeding 0.5. But if you leave from the lower half, it is not reaching 50%. If you leave from the upper half, it is not reaching the 50%. So 4 will be the median here. Is it okay?
Yes, sir.
Okay, then see you tomorrow. All the notice of exam is uploaded in your MS Team. Please follow it, study well. Tomorrow we will have 2 definitions and we will solve some problems from random variable and any other thing, whatever necessary problems, interesting problems we will try to see tomorrow.
Sir?
Yes?
Sir, moments of random variable is also in the syllabus of this test, no sir?
Whatever we have covered.
Okay.
Moments,
whatever we will cover till tomorrow.
Till tomorrow, because the thing is that if you see the syllabus, first day the syllabus given, in probability section so many subtopics are written, random variable section so many subtopics are written, both of them, all of them are incorporated.
Okay sir, thank you sir.
Thank you, sir.
Thank you. Chalo, see you tomorrow.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you sir.
Thank you.
Thank you, sir.